In this video, we are going to explore the frontiers of the universe by getting a brief overview of what is string theory and loop quantum gravity. What role do these two things play in understanding quantum gravity? Right, so quantum gravity is an active area of research in theoretical physics, and it seeks to unify general relativity and quantum mechanics. Now, these are two of the most successful theories in physics, and in this video, we're going to provide a brief overview of the two main approaches towards quantum gravity, which is general relativity. I apologize, it's not general relativity. What I meant to say was quantum gravity. So we are going to provide a brief overview of the two main approaches, which is string theory and loop quantum gravity, right? So these are two of the approaches that we do to understand quantum gravity. Now we are going to discuss the fundamental building blocks and the key features of each of these approaches. Again, the approaches are string theory and loop quantum gravity. These are the approaches towards quantum gravity in general. And we're also going to talk about their potential to unify all forces in the universe. We'll also highlight some of the challenges that researchers face in developing a complete theory of quantum gravity. Some of these challenges or problems include singularities and lack of experimental evidence as well. Overall, quantum gravity remains one of the most important and fascinating problems in modern physics, with far-reaching implications of our understandings of the universe. Now, the unification of general relativity and quantum mechanics is one of the most challenging problems in theoretical physics. General relativity describes gravity as the curvature of space-time. However, quantum mechanics deals with the behavior of matter and radiation on the atomic and subatomic level. The combination of these two theories, general relativity and quantum mechanics, is what we call quantum gravity. Now, quantum gravity, it seeks to explain the behavior of the universe at the smallest scales where the effect of both gravity and quantum mechanics are significant. The current understanding of quantum gravity is based on two main approaches. As we have said before, these are string theory and loop quantum gravity. Again, in this video, we're going to provide a brief overview of these two approaches, and also we'll discuss some of their key features. So let's start with string theory. So string theory is a theoretical framework that attempts to describe all of the particles and forces in the universe in terms of tiny one-dimensional objects, which we call strings. Now, according to string theory, these strings are going to vibrate at different frequencies. And that is what gives rise to various particles in the universe. Those different frequencies can be interpreted as various different particles inside your universe. Now, the fundamental building blocks of string theories are strings themselves, right? And they're assumed to be extremely small. So small that they're of the order of the Planck length. And what is the Planck length? It is written as L subscript P, which is equal to the square root of h bar g over c cube, which is approximately equal to 1.6 into 10 raised to power minus 35 meters. Right? Here, h bar is the reduced Planck's constant, g is the Newtonian's gravitational constant, and c is the speed of light. And this Lp is the Planck length, which is so small that it is of the order minus 35. Right? So it is at this order where strings dimensions lie, right? So strings are so small that they're of the order of the Planck length. Now, the vibrational modes of the strings are going to give rise to various particles in the universe, as I mentioned before. And these particles even include the graviton, which is the hypothetical particle that mediates the gravitational force. It is hypothetical since we have no evidence of it being existing, right? We have not seen this particle, but it is just a hypothetical particle. Now, in string theory, gravity is not a fundamental force, right? So that's the punchline. that gravity is not a fundamental force, but it rather emerges from the interactions of these strings, right? So here you can see a particular string, right? And if you have multiple strings and these strings interact with each other, that's what gives rise to gravity, right? Now, one of the most significant features of string theory is that it requires the existence of extra dimensions, right? Beyond our understanding of the three basic dimensions of space and one dimension of time. So we understand four dimensions very well. Three of them are spatial and one of them is time. But string theory requires even more extra dimensions, and these extra dimensions are compactified or curled up on tiny scales, making them invisible to our eyes, right? At our macroscopic scale, this appear to be invisible. Now, the compactification of these extra dimensions is believed to play a crucial role in determining the properties of the particles and the forces in our universe. With that, we can move on to the equations of string theory. And these equations of string theory are incredibly complex. And in fact, the string theory itself is not yet fully developed, right? So it's still in the making. However, the theory has the potential to unify all the forces in the universe, which includes gravity, into a single coherent framework. Now, I'm going to write down the action of what is called the bosonic string theory, just for the sake of the beauty of it. So we know that you can write action with S, and the action for the bosonic string theories is as follows. It's 1 over 4 pi times alpha prime integral of d squared sigma under root of minus g times g a b partial a x mu partial b x nu eta mu nu plus some other terms, right? Now, in this action, this is the action of a bosonic string theory. And in this expression, this g that you see that is under the square root, it is the determinant of the metric tensor, which is over here GAB. That's the metric tensor. Again, I'm assuming that if you are watching this video, you have some basic knowledge about general relativity, special relativity, and you have an understanding of tensors as well, right? Now, this metric GAB is defined on the string world sheet, as we call it. And these x mu and x nu, these are the space-time coordinates. Note that I say space-time because these coordinates carry both time and spatial dimensions in them. So x0 would be time coordinate, x1, x2, x3 would be the spatial coordinates such as x, y, and z. What about alpha prime? Alpha prime is a parameter that is related to the string tension, right? So if you can think of it as a similar tension that if you have a sheet and you put a mass on that sheet, then there would exist some tension in the sheet. Or for example, if you are hanging by a rope, then there is some tension that develops in that rope as well. So it's a sort of familiar with that, right? Now, like I've said, that the vibrational modes of the strings give rise to various particles in the universe, like graviton as well, right? So just for the sake of it, I have written the action of bosonic string theory over here. So I'm just going to put this thing over here. And now we can move on to the next page, where we will start our discussion on loop quantum gravity. Now, loop quantum gravity is another approach to quantum gravity that is based on the idea of quantizing the geometry of space-time itself. So you quantize the space-time itself, right? So in this approach, space-time is now no longer assumed to be a smooth continuous manifold. So it's not that anymore, but it is rather composed of discrete granular structures, which we call spin networks, right? And I'm going to show you spin networks in the next page, but we'll get to that in a bit, right? Now, in loop quantum gravity, the gravitational field is described by a connection, and that connection is A. I'll just call it A for now. And we also have a conjugate variable, which is E. So we'll get into what these things mean in a bit, right? Now, this conjugate variable and the connection, they represent the geometry of space-time, right? So if you have these two variables, connection and the conjugate variable, then you have a basic idea of what the space-time's geometry would be. Now, these variables satisfy what is called the Gauss constraints and diffeomorphism constraints, which ensures the consistency of our theory. Now, I'm going to write down the Gauss constraint. Again, just for the sake of it, the Gauss constraint is written as GA, which is equal to partial A times this variable, this conjugate variable that I talked about, E, AB. Right? And the Gauss constraint is that this thing is equal to 0. Right? Now, this EBA, this thing, it is also known as a spatial trade, right? So it's a spatial trade. And if you're familiar with general relativity and the study of gravity in general, then you know what I'm talking about right over here, right? The spatial trade. If you're not familiar with these things, and you're just watching this video for the fun of it, then I'm trying not to include as many equations. But of course, if you're talking about something like this, then having equations is kind of a necessity, right? You cannot get rid of all the equations. Anyhow, I'm now also going to write down the diffeomorphism constraint, and the diffeomorphism constraint can be written as HA is equal to FIAB times EBI. And this thing is approximately 0. That being 0 is the diffeomorphism constraint. Now, over here, this FIAB is what we call the curvature of connection. The curvature of connection that we called A, right? And EBI is just the inverse now of the spatial triad, right? So EBI is the inverse of this thing. All right. Now, these constraints basically generate the dynamics of the theory, right? And they ensure that the theory is background independent. So it does not depend on the background that we are using for the theory. It is completely background independent. One of the key features of loop quantum gravity is that it predicts over here, it predicts a discrete quantized spectrum of areas and volumes for the space-time, right? This is in contrast to what we see in general relativity. In general relativity, we assume that space-time is continuous and it can take on any value, right? However, again, in loop quantum gravity, it predicts the space-time as a discrete quantized spectrum of areas and volumes, right? So in loop quantum gravity, the area and volume are like operators and they have discrete spectra. And I can write down these operators for you. So it would be an eigenvalue equation for both of these operators, area and volume. So, you know, in general, if you have any operator O and it acts on a state V, then you get some, I'll call it lambda, the eigenvalue, and you get the same state back, right? So this is your general equation, general eigenvalue equation. For our case, we have two operators. One is area and the other one is volume, right? So for area, we can write this eigenvalue equation as A acting on some state. These states that I'm going to write down for area and volume, these are called the spin network states. So this state that I wrote, state gamma, this is a spin network state, right? And the area operator acts on this spin network state, and it gives you the eigenvalue for area as 8 pi times this the spin network state value and multiplied by L squared. This is LP, by the way, the Planck length squared. And of course, you get your same state back. So this is the area eigenvalue equation. What about the volume eigenvalue equation? The volume eigenvalue equation also acts on a spin network state. This time I'll call it mu. This is equal to 4 pi mu LP, and this time LP is cubed, divided by 3 times the state mu. Again, this gamma and mu, these states, these are called the spin network states, and LP is just the Planck length. Right? Now, the fundamental building blocks of loop quantum gravity are spin networks. Over here, you can see I have shown a spin network. This is one of the representations of the spin network drawn by Sir Roger Penrose. And these spin networks are basically graphs that represent the discrete geometry of space-time. Now, the edges of this graph, as you can see, they represent one-dimensional connections, while the vertices of this spin network or this graph represents the three-dimensional volumes, right? Okay, now the dynamics of our theory are determined by what is the evolution of spin network states. You know that when you study quantum mechanics and you understand the evolution of states, you do that by acting with the Hamiltonian operator on a state, and it shows you how the state evolved, right? So, Hamiltonian operator plays an important role, right? So, even in this theory, the dynamics of it is covered by the evolution of the spin network states, and that is governed by the Hamiltonian constraint, right? And what is that Hamiltonian constraint? This Hamiltonian constraint is that your Hamiltonian operator acts on a state, let's call it psi, and that is equal to 0. So when the Hamiltonian acts on your state, this state psi, by the way, is the quantum state of the entire universe, right? So again, the Hamiltonian constraint is just that when you take your Hamiltonian operator and you act it on the quantum state of the entire universe, it just vanishes. So that is what is the Hamiltonian constraint. And the dynamics of this theory is determined by the evolution of spin network states. But this evolution of spin network states are governed by this Hamiltonian constraint. Now, finally, let's end this video with some concluding remarks. So we're going to conclude this with, I'm going to start with saying that quantum gravity is a theoretical framework that seeks to unify general relativity and quantum mechanics. That's what we have seen so far, right? And the two main approaches to quantum gravity are string theory and loop quantum gravity. So these are the two main approaches towards quantum gravity, right? So here, these are just some of the key things that you're supposed to take away from this video, right? Now, string theory describes gravity as the interactions of tiny one-dimensional objects, which are the strings, while loop quantum gravity quantizes the geometry of space-time itself. Now, both of these approaches have the potential to unify all forces in the universe, including gravity, into a single coherent framework.